Hello friends, welcome to today's class. This is your Professor Vinay Sangolli. And moving ahead from the previous classes, today we will go ahead one topic ahead and today we will move ahead from your threshold logic and linear neurons. So friends, in all the previous classes, we have seen various algorithms. To name a few, the famous ones is perceptron and LMS learning algorithm. So we have seen various versions of your LMS learning algorithm as well. So if you observe these two algorithms, what did we come across? We saw that these algorithms were working based on your single binary threshold neurons. So I hope you remember we called them as TLNs, right? And sometimes we also used only linear neurons. Okay, so that means both these algorithms, that is perceptron and various variants of LMS algorithm, were working using your TLNs, right? And what we are doing with these TLNs, or what we are doing with these algorithms in addition with TLNs, we were trying to do data classifications. We're trying to classify the data. Like say the best example we saw was say a general layman's example. I want to classify stars from squares. I want to differentiate stars from squares. So while doing that, we came across two problems. One is sometimes your data set was linearly separable. Sometimes your data set was what now? It was not linearly separable. So we saw all these things in the previous classes. But moving ahead, we had some problems in these algorithms. The next topic we saw was we were trying to correct our errors. How we tried to correct our errors? With the help of one way was what? Your linear error correction model. The other way was your gradient descent algorithms, or that is by using the gradient descent method, right? So these two main things we learned, that is how to correct an error using your error correction and gradient descent procedures. Then going forward, how did you say that it was a TLN, or how did you say it was a binary threshold neuron based on your signal function? So that means the signal function we were using is binary signal function. Then the next of very important thing we saw was there we saw a single layer architecture. We are not concerned, or we are not much worried about how many layers are there. But but now we need to move ahead from this single layer. Why? Because we want to do much better classifications. I mean to say the classifications which are a bit difficult. So in that case, this single layer neuron model will not be helpful. And as you already know that if I go on adding n number of layers, but if I keep it as the linear neuron, then it will not help. That is, even though I have a multi-layered linear neuron network, we say it is very much equivalent to your single layer linear neuron network. So therefore, we would not be interested in using these linear neuron models. We want to move ahead, and so if I want to move ahead, what is the thing I need to do now? And why we are moving ahead? We are moving ahead because the computational capabilities of these earlier algorithms were not that efficient. So we want to increase the efficiency of these algorithms. So therefore, if I want to increase the efficiency of your algorithms, then the first thing I need to do is I need to smoothen the nonlinearity. You might already observed that there will be nonlinearity in your all neural networks. So what we'll do, first we'll introduce the nonlinearity, but how should be the nonlinearity? It should be very smooth. Next important thing, the next point I have mentioned here, you can observe the sigmoidal signal function we'll be using. Till now we have used what now? Your binary threshold activation function. Now we will be using your sigmoidal signal function, and I hope this has been already covered in the previous first module wherein we have studied various signal functions. Next very important thing we'll be doing is we'll be starting to layer the neurons. That is, we will go ahead with the network architecture. Till now, we are not worried about your network architecture, but henceforth, we'll try to introduce the network architecture. And how this network architecture is obtained? By introducing layers of neurons. So that is what we'll be doing. We'll try to introduce the layers of neurons. So these 3 points are very important. And why we are doing all these 3 points now? To increase the computational capability. Now, that means when we create a network, what is the expectation out of this network? The expectation out of this network is to approximate the function. The meaning of approximation is it should try to find the value of that function. How it can find the value of that function? The network will be given with your input output relation, and it will be also given with a training set, which is d of k most of the times. Then using these two things, it has to find the function. I mean to say for example, I'll be giving you a set of datas, like the x data is 2, 4, 6, 8, and the y, which is output, is somewhere like say 2 square 4, 4 square 16, and so on. So that means I will be giving you input and output relation, and I'll be giving you a training set, but I will not be giving you what is the function. So based on these two things, that is input output relation and training set, you need to find, or you need to approximate the function which is being used in order to get the output. So this is the work of your network. So our network is expected to do these things. So I hope I'm clear, friends. So these all things, if I want to do, then we need to be going through our next algorithm. Before that, we'll try to see how our network looks. So this is how our network will look. It will be majorly consisting of 3 layers, which we broadly classify them into an input layer, hidden layer, and output layer. This we have already seen in your previous module as well. This is just a recap. So in the input layer most of the times is a single layer. The hidden layer can be one, or it could be more than one. Output layer is also most of the times a single layer. As you can observe in the diagram, we also have bias neurons. These bias neurons help us to generate an internal signal, not using the external input, and it is usually a plus 1, right? So here the input layer has n linear neurons that will receive real valued external inputs in the form of n dimensional vector in the region R of n. So this layer, what it will do, along with this input, whatever we have taken, along with that, it will be also using the bias neuron. You can see there, bias neuron is feeding in your hidden layer, right? So the hidden layer has your sigmoidal neurons that will receive the signals from the input layer. Remember, friends, hidden layer has sigmoidal neurons. Okay, and the next very important thing, your output layer. Your output layer will also be having the sigmoidal neurons. Say for example, if I have q sigmoidal neurons in the hidden layer, then the output layer would be having some p or r sigmoidal neurons. Okay, and how is the network arranged here then? We have basically two types of network arrangements. One is feed forward and another one is feedback. As you can observe here, it is nothing but the feed forward type of network architecture, right? So why is this whole network used? So to give you a simple example, let us look ahead with this small diagram. Okay, so if we see the small diagram, what we have plotted a curve. This curve is giving you some function, that is, it is obeying some function. So we need to find out what is the function the curve is obeying, depending or by taking into consideration your input output relation, as we have seen just now, and the training set. That means the network would approximate the function with the help of your input output relation and the training set. So the diagram which you can see here is the function of f of x is equal to x into e raised to minus x. That is, it is x into e raised to minus x. So by seeing your input output relation and the training set, our model, that is network model, should find out that the function is x into e raised to minus x. That means the questions which arise here are how the network architecture will learn the accuracy. That is, what is the network architecture required to learn with sufficient accuracy so that it will represent a function by only a finite set of data. There are not a number of data sets here, it's a limited. That is the first question. Next thing, will the trained network predict the values correctly for unseen inputs? We have seen that you might say that I will give you a set of inputs, but what if the inputs are changed? After training the network, what if the inputs are changed? Then also our network must be able to find the correct function. So these two are answered with the help of two important things. One is approximation and another one is generalization. What is approximation then? In approximation, the whole network will try to learn based on the patterns and the training set. So it will try to approximate. How it tries to approximate? Based on the training set and the patterns which you are feeding it. Next very important thing, the next very important question you asked was, will it predict correctly for unseen inputs? So there comes generalization. That is, our network must be generalized. It should have the ability to, of a trained network, to predict correct outputs of the function. Whatever function you give to your network, it must be able to find it correctly. That is nothing but your generalization. Then the next very important thing we see was, how does this happen? How does this do then? Then in order to do this, we'll come across a function called as universal function approximation. What this does then, here in universal function approximation, we try to increase the number of hidden layers so that it could easily find out the proper function. That means we are trying to increase the complexity. Remember friends, when you try to increase the complexity, the computational also increases. So to define your universal function approximation, it goes something like this. It is a network which is complex. That is, it should include sufficient number of hidden layers. What are hidden layers now? Hidden layers are nothing but your hidden neurons. Okay, so this is very important. So till now we have seen the various needs of your multi-layer network architecture. You can see what we are studying. We are studying the multi-layered network architecture. What is the need of this multi-layered network architecture? So that means, what all did we change in this whole today's class? We changed the first thing, our signal function. You can observe the signal function which we are using is being changed from your binary threshold neuron into a sigmoidal neuron. That is sigmoidal signal function. Right. The next thing is what now? You increased the number of neurons. That is, a layer of neurons were introduced. You can see here, you have introduced a layer of neurons, right? So this is the second thing we did. Then the most important thing, or the most fortunate thing, what we are saying is, we are still using our earlier method to reduce the error or to find the error. What are those earlier methods? One is error correction and another one is gradient descent. So we will be using your gradient descent procedure. So based on all these three things, the new need arises. That is, we should go ahead with the new algorithm which would take a different signal function, which would introduce the layers of neurons, and which would take into consideration your gradient descent. That new algorithm, we call it as nothing but backpropagation learning algorithm. So friends, this is very important. Backpropagation learning algorithm. So remember here friends, backpropagation learning algorithm makes use of different neurons, right? It also makes use of n number of layers, or you can say it makes use of at least one hidden layer. Then very important thing, how it tries to correct the errors with the help of the gradient descent procedure, right? So before moving ahead with your backpropagation learning algorithm, most of the times it is asked in your video examination, so please go through this thoroughly. We would like to see what are the notations which are being used in your backpropagation learning algorithm. The notations we will be using are as follows. So first thing is nothing but it has an input layer, it has a hidden layer and output layer. That means we'll be having three layers. Next very important thing, which are the neurons which are used in these layers? In your input layer, the neurons we use is a linear neuron which is given by del of x is equal to x. Right? The hidden layer and the output layer neurons are sigmoidal. So which is given by your sigmoidal function which you already studied in your module number 1, which is del of x is equal to 1 plus e raised to minus lambda x. So these two things are very important. Apart from that, any scalar or any vector will be always subscripted, right? And what is the subscription use? The subscription use will be the number of times the iteration is taken, which is usually we take it as k. Like we say delta x of k. It means what now? That the activation has been iterated k number of times, that is n number of times, k number of times, something like that. Okay. So before going ahead, we will see some more notations. So if you can observe here, input stands, IP stands for input, hidden stands for hidden layer, OP stands for output layer. So the number of neurons in your inputs are n plus 1, that is n is being used for your input, for hidden q plus 1, and for output p. The signal functions we use are linear in your input layer, sigmoidal in the hidden layer, and in the output also sigmoidal layer. And the neuron range, index range, is from I is equal to 0 to n, h is equal to 0 to q, and j is equal to 0 to p. And the weight, how do you update the weight, which is very important. In the previous chapter we have just seen the weight updation equations, recursive weight updation equations. So how do we update the weight, which is nothing but from I to h, wi of h, from h to j, it is w h of j, right? So we have seen all these things, but one major thing we still need to do is how our training pattern works, that is how our training vectors work. So our training vectors is given by q. So you can observe here the training tau is given by x of k, which is input, and d of k, which is nothing but the output vector response desired when your input x of k is represented, and k is equal to 1 to q is nothing but the number of iterations which starts from 1 and it ranges up till q. So these are some of the notations which we will be seeing in your backpropagation algorithm. Please go through this part of the video once again, so that the same notations will be used throughout the whole algorithm. Okay, so moving ahead, this is one more very important thing. We were speaking of error correction, right? So always remember, friends, the linear error is not so useful. So therefore we would like to get a squared error, and you have already seen how a squared error is obtained. So what we are trying to do in the whole thing now, we are trying to get the vector pairs in your training vector, right? So we will be using these training vectors, and we'll be using the input samples in order to find an unknown function, which is f, and from the region where r of n to r of p, right? So that means we wish to find the neural network so that it would approximate the function, right? So that means you would be using the gradient of the linear pattern to reduce the global error. That is, you will take a single error pattern, use its gradient, and try to reduce the global error. And how do you do all these things? This is done with the help of changing your weight. Remember, again we are moving to changing of weights. Of weights of what? Of nothing but your training pairs. Training pairs are nothing but x1 of d1, x2 of d2 up till xk of dk. And from where these training pairs are taken? These are taken from the training set. Now, so before moving ahead, what we are trying to do actually then, we will take the input pattern, which is x of k, we will feed it into a neural network n of k, right? So what we will do, we will take the input pattern x of k, we will be feeding it, we will be putting as an input to your neural network n of k. And how is this n of k obtained? N of k is obtained by iterating your neural network k times. That is, first you will get n1, from n1 you will move to n2, from n2 you will move to n3, from n3 finally after iterating k times you will move to nk. Then, right, so finally what you do, using your x of k and your n of k, you will be getting output vector, signal vector, which is del of yk. So remember, friends, del of yk is different from yk. What is yk here? Yk is nothing but the vector of activations of output layer neurons. Okay, so this is what we will be doing in the whole updation procedure. That means your instantaneous error for the kth training set is given by E of k is equal to d of k minus del of y of k. Now, what is this d of k? You already know. What is del of yk? This also you already know. It is nothing but the output signal vector. What is this d of k? It is the predicted output, right? So then what is E of k? E of k is, just now you have seen, how do you find the E of k? You apply the gradient of the pattern error so that you reduce the global error. What is the pattern error? The small e's. And what is the global error? The capital E, right? So the small e's is given by E1 of k, which is nothing but it is equal to d1 of k minus del of y1 of k, right? So that means you can say this E1 of k is equal to the first term. Similarly, E2 will be having one more term here. Similarly, EP of k is equal to nothing but dp of k. This whole thing is nothing but your E of k. This whole d1 of k is nothing but your d of k. And this whole del of y1 of k, y2 of k, yp of k is nothing but your del of y of k. So I hope I am clear, right? So moving ahead, so you have seen your equation 1, equation 2, we'll go to your equation 3. So as you can see, this is your normal error, but we are not interested in your normal error. We want a squared error, and you already know how a squared error is given. So this is nothing but your instantaneous sum squared error, which is given by E of k. It is nothing but the sum of the squares of individual output error E j of k scaled by 1/2, right? So if you observe this previous slide, you know what is it? What is your previous slide? It is d1 minus delta y1 of k. So the same thing has been used here, right? The same thing we are using here, that is dj minus del of yj the k. Then we square it and divide it by half, which is nothing but half of ek transpose into ek. You already seen it. It is nothing but like your correlation function vector. Okay, so that means the mean square error we have calculated already, that is E of k. But this mean square error has to be applied on what now? It has to be applied on the entire training set, which is given by tau. And where is this training set applied? On the specified network, which we give it by n. That means your E is nothing but 1 by q, k is equal to 1 to q, and E of epsilon of k. That means the whole error, that is epsilon, is nothing but summation of your individual epsilon of k, and which is applied over k is equal to 1 to q iterations. K starts from 1 and up till q iterations. So thank you friends. So this video forms the basics of your backpropagation algorithm. So please go through this video carefully once again so that you will understand the whole backpropagation algorithm. Okay, so we'll meet again in the next class. Thank you.